Hello everyone, welcome to PyTorch career tutorial sessions. So this is fourth session in the tutorial list, and we will talk about how to use MMF for knowledge-based recommender systems. So this is a joint presentation between me, Amanpreet, and 𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏, and we are both research engineers at Facebook AI Research. So today's agenda will cover three things. We will talk about MMF, gives an overview of it, and then we'll create an OK-VQA dataset inside MMF and show how exactly you can implement your own. And then we will show an implementation of a new novel model MMF transformer from scratch, and which will give you an idea of how to implement your custom models inside MMF. So the code for this tutorial is available at the collab. There's a QR code which you can scan to follow along with us. So let's start with what exactly is MMF. So MMF is an OSS multimodal framework, which is a research framework for vision and language research. And you can do any kind of research on any of the vision and language tasks that MMF supports. We have 20 plus of those. And we also have the state-of-the-art implementation for multiple of these models that work best on these tasks. So this framework also has a lot of training utilities that can help you to avoid all of the cost that happens and for every time you start a project from scratch. So MMF has a vibrant community on GitHub, and we welcome you to contribute or have a look at MMF on GitHub. So let's talk about what do we mean by a vision and language task here in the context of MMF. So a simple definition will involve like any task that involves a visual and textual component and then requires the reasoning of a bot to solve it. So these tasks, they can't be solved by just by vision alone or just by text alone. You need both of them to answer them. So let's ground this into a framework which we'll be using throughout this tutorial. You have an image and a text. You pass them through a model, and then you get an output back. This is a scenario we will be working on. The model is a black box, which we will implement, and how do we get this image and text, that also we will implement in MMF. So let's take an example of a particular kind of vision and language task that we just talked about. So that's visual question answering, one of the most popular one. So what does this task involve? So an image is given and a question is also given based on that image. So you have to like understand the image and then answer the question based on things in the image. For example, if the image is given alone, it doesn't make sense without the question, like what exactly you need to answer. And then if the question is alone, there is no context on what to answer. Then text VQA is a special case of VQA where you need to read text in the image to answer a question. And the dataset that we'll be implementing, OK-VQA, outside knowledge VQA, is also a special case of VQA where you need outside knowledge, some knowledge source or some outside knowledge to answer the question that is present here. We will see examples of OK-VQA later. So here you can see like on the board, there is written like left lane closed. If you read that, it should be easy to answer from the model, like that the answer is left. This is the way these models work on VQA. They take in an image and a text and just classify them into like a number of answer options that are there. MMF contains a lot of these data sets which can broadly be classified into 5 categories. Visual question answering, we have like multiple of variations of visual question answering, visual genome clever, then image captioning where you have to generate a caption for an image. Reasoning, these are pure reasoning tasks which require reading both image as well as a text to answer something about this particular scenario. Then dialogue, which involves a dialogue over the image, and integrity classification, something like classifying a meme into hateful or not hateful. So MMF is a multimodal framework built for fast VNN research, and we have successfully used it into multiple projects in past. So what makes MMF so special, and why should you care about it? All components in MMF are PyTorch powered, which means that all of the knowledge that you have about PyTorch, you can use it here as well. MMF basically involves less boilerplate. we do give you all of the utilities out of the box, like distributed training, checkpointing, early stopping, and everything else. A lot of metrics implementation outside of the box. It's powered by PyTorch, and it's modular and composable. You can take only the components that you care about. You don't need other components. You don't need to use them from MMF. You can use MMF as a library. For example, you only care about the model and you want to test it on your task and don't want to use MMF. That's easy to do. So let's dive in a little bit into our collab tutorial, understand how we are going to implement this data set. So how do the dataset work inside MMF? Let's take an example of the visual question answering task. You have an image and text. You pass them through a processor. So processor is a concept inside MMF which takes in something and just outputs something that has like a variation of the input text. The processors can be used for like various kind of things. It's basically a reusable block inside MMF that many datasets can use. For example, there can be a glove processor which converts the words into indices for the glove vocabulary, and or it can directly give you glove vectors as well. Same for bird. It converts it. The processor can convert the given text inside into the indices of the bird vocabulary, and then you can map them to the bird embeddings. Then the examples goes on. And some examples of from other frameworks are like torch vision transforms, which is same reuse set of processors that can be used anywhere. So the data goes through a bunch of processors to come into the format that MMF models can accept. You pass them into a sample, and then a list of sample basically creates a sample list which is sent to the model. So let's start implementing this data set inside the collab. So in this tutorial, we will show like how we can use MMF to build a knowledge-based recommender system. So let's start with setting up the OK-VQA dataset. So before we dive into details of OK-VQA dataset, let's set up some prerequisites for MMF. So we have enabled the auto reload here so that every time you add a new module, you will if you don't need to like rerun the runtime, it will automatically re-import something at all of the modules, and it will give you the fresh copy. So we can start from like git cloning the MMF, and you basically will clone it inside the content directory. So it gives me an error because MMF already exists. I have already run this collab notebook once, but in your case, it will basically clone it from scratch. Then we install some specific versions of Torch and Torch Vision that MMF requires, and because Collab has some different ones. And then we basically set up the MMF in develop mode so we can edit it. And we also upgrade some dependencies which are very old inside Collab, just for the sake of it. Because these are already installed, it will just say requirements are already satisfied, and then we can move to the next thing. So you can see that the specific version of MMF has been installed from source, that is release candidate 11. So before we move into dataset, I want to like talk about the three components that are needed to implement a dataset. So first is an annotation database, which will basically load the annotations that are provided by datasets. So each dataset has its own kind of annotation files. So you need a kind of like a wrapper, which will convert it into the MMF format, and so that is easily consumable by MMF in any form. Then you also need an image database, which is already provided by MMF, but can be overridden if something is needed for the specific use cases. So another thing that I want to note is like our example annotation database is already provided in MMF, which can import various kind of existing file schemas like JSON, JSON-L, but sometimes there is a customization need that is needed, so that you will need to implement custom annotation DB in this case, which is the case for annotation DB. Then you finally need to implement a builder class, which will be registered to MMF using MMF's registry, which returns back an instance of torch.util or data set, and MMF will use it to load the data, which will be passed to the model. So let's first check like how does the OK-VQA dataset actually look like. Let's just go to the OK-VQA website and have a look there. So you can see this dataset is outside knowledge visual question answering, and there are some examples which require using knowledge that's not available in the image to answer these. So it has 14,000 questions, and it comes in like two forms. One is annotations and one is questions. So questions contain only the questions, and annotation contains everything else that is required, and the uses images from Coco. So we can like see an example of how exactly this looks like inside our collab. So let's run this, like wget the annotations, extract them, and also the questions, and then extract them. And here we will just print out the annotation keys and the image ID. So here you have like an question like what sport can you use this for, and the answers are like racing, and then racing, and so this might be a car in the picture and is asking like which sport you can use this for. So that's how the format is, basically a question in a separate file and answers in a separate file. So the next thing is to like create the annotation DB itself. So annotation database is already provided by the MMF. So you only need to override a particular function for your use case, that is load annotation DB in this case. So because we have two paths, one for annotations and one for questions, we need to like pass them together as a joint string by comma so that we can pass them both together. So we split the path here into two paths, and then we make sure that we have two paths, one for question and one for annotation. We load them both. And if the annotation is present in the path 0, then the annotations are actually the path 0. Otherwise, the path 1 is the annotation. Now, what does this load annotation DB expects us to do? It expects us to like create an array, a list, which basically contains samples of all of the annotations that are present inside the data set. And we need to assign it to the data attribute for this data set. So we start with creating a list, and then we create a question dictionary, which points each question ID to a question. And then we start passing the annotations. We take in the question from the question dictionary, and then we take in the answers from the annotation itself. Then we join them together into a single dict. So question and answers are in single dictionary now, and we append that to the list we have. Then we assign that to cell.data, and now this torch dataset in this get item function where the IDX come, we can just return cell.data, the IDX index of it. So you can basically return that as a sample itself. So before I move further, there's something we need to talk about. So MMF is a configuration first framework. So everything inside MMF is based on config. Why do we do that? So the reason of doing that is like we don't want to change code for anything small that we change. For example, you change a loss function. You don't want to go inside the code and change the code to like pick up a new loss function. Same for the model, like different data sets should be easily be usable with different data set, but just by making the configuration changes. So let's see how does MMF configuration system works and what is the hierarchy here. So we by default provide a config that is in /config/defaults, which contains all of the default parameters, something like training, snapshot interval, what are the maximum updates that are required, the batch size, then something around checkpoint and distributed. Now after this, like specific stuff comes like something like dataset and model configuration, which are very specific to the use case you are implementing. For example, like for dataset config of VQA2, you can have features for train in some LMDB and some as other LMDB. And similarly for model config, like MMBT can have its own parameters which are different from other models, like hidden size, how many number of layers drop out. So we do provide like default configs for each of the models and each of the datasets that we have, but you can override them in the user config, which comes in higher priority than the previous one. So you can maybe update the feature train path to something like URLMDB, which is your custom features. Then you can change the hidden size of MMBT to 1024 if you don't like the default 768. And you also can change something in the default config like training.batch size. So we also provide like command line ops, which you can use to override anything that's present inside the configuration from command line that allows us to like faster iterate over the versions, and you don't need to actually go inside the configuration and change stuff. You can just update it from configuration. This is also like very helpful for running sweeps, where you can just pass your options multiple times and run sweeps and don't really need to change the configuration. So let's come back here to the dataset in implementation. So now we will actually implement the OK-VQA dataset, which will inherit from MMF dataset, which expects us to like implement a get item function. And MMF dataset is basically a 𝗏𝗏𝗀𝗃𝗃𝗃 dataset which implements something specific and something required to interact with MMF models. So we have some helper methods inside that will help you to automatically download stuff or something else, and a lot of other utilities. So it also builds annotation DB, the default annotation DB on default settings. But in this case, because we have our own custom annotation DB, we will override and make sure that we return OK-VQA annotation database that we implemented here. So we are overriding this, and if you override image or feature database, you can override those specific things. So we are making sure that we get the correct annotation path here and just passing it to the OK-VQA OK annotation database. So then we have a helper function to convert image IDs into the actual image path for Coco, which is basically filling it with zeros till 12 and just based on train or validation, it's returning the correct JPG. For the image for the processors, we can just call default processors from init processor from the MMF dataset, which will init each of the processors present inside the configuration. Since we are config first, we also define processors through configuration that allows us to change processors on fly. For example, I can run an ablation on glove, and then I can run another ablation on BERT embeddings, or I can run another one on Elmo just by changing the configuration and no code change. But in this specific case, because our image processor needs to be assigned to transform, we are overriding this init processors method. So the transforms, the image DB transforms, expect them to be assigned at runtime. So in the get item method, we just take the sample info from the annotation DB we just created, like we talked in past. We passed in the IDX and we just created, and then we initiate a sample instance. Sample is a utility provided from MMF, which is a format you need to return the sample from. You need to return the data from get item, and then you basically pass the text, like the question, inside the text processor, and then you just update it into a current sample. So sample is a dictionary, so you can update whatever this processor returned. It also returns a dictionary. The signature of processor require that they take in a dictionary and return back a dictionary. So then you also assign the ID, and then you get the image path, and you basically use the image DB to load the path, load the image, and just assign it to the sample. Then if the answers are present inside the sample info, we use an answer processor to process the answer into a VQA format, making sure everything has like 10 and we have proper scores assigned, and then we assign the targets to the answer scores. This will basically provide score for each of the answers in vocabulary. So VQA is a classification task where you have like a fixed vocabulary for answers, and you basically tell like this answer in the vocabulary has the highest probability of being the answer, and targets tell you like what was the actual probability of these things. And most of the models expect targets to be there because that's your output and how the loss will be calculated and loss expected. Then we implement a visualize method, which will basically print out the question and visualize the images that are present here. The final step here is to actually register the dataset to MMF. That's done through the dataset builder. So the job of the dataset builder is to actually return the instance of the 𝗏𝗏𝗀𝗃𝗃𝗃 dataset. And because we set the dataset class to OK-VQA, we can just leave everything else to the MMF dataset builder. It will take care of automatically downloading stuff and everything else. The config path is a config we created. That's the config default config for this dataset. And now because we already have the config present on GitHub, we will just download it and see how exactly it looks like. And this is how it prints. So you can see like text processor is a vocabulary which uses like glove embedding and everything else, and the annotations are in a proper format and how MMF expects them. And then you basically have train inside. Okay, so this is a directory structure for MMF that it expects for most of the data set. Like this is the variation and this is images. So you can read more in the MMF documentation on to understand how exactly a data sets directories are expected. So you can say like use images is true, that will initialize image DB, and if you say features is false, then it won't initialize the feature DB. So MMF can work on features as well as images. so it's model dependent. So then you also specify which thing to automatically download, and then answer processor and image processors like center crop. These are the same as the torch vision transforms. So this is actually a zoo config, which you can add to the separate zoo, which will make sure that whenever this command is run, it will automatically download OK-VQA. So the zoo config is defined inside the builder class so that it knows where to find the exact URLs to download the exact data. So we have already added all this. We can dump it inside the zoo. And now what we can do is actually visualize one of the examples from this data set. Finally downloaded everything that's required. And you can see examples of actual OK-VQA data set, like you see who designed the statues for this particular thing. This might be some famous statue. And there are other things like what is the purpose of the cubes in the picture. And you can see them here. It's like sitting. And what kind of plant is seen in this picture. You can see this plant. So all of these are like required external knowledge, which is not present inside the data set, inside the image itself. Like what type of event might the couple be preparing for? We can run it once more and just see more examples, but then afterwards I will hand it to Vedanoj. So here are more examples. It says like what appliance is in the background of this picture. So you have to like see what exactly this is. And there are other questions like what do you feed this kind of animal like this horse? You have to tell that. So now I will hand it over to Vedanoj so that he can go over the model part and we can move to the next part now.
Thank you, Aman. So I'll share my screen now. Okay, hey everyone, I'm Vedanoj. So I'll walk over the building the model part. So let's first see how MMF datasets connect to the models. So let's take an example, the same example that was shown earlier. We have an image here and accompanying a text, a question. So, and then also maybe other modalities, excuse me. So the image will pass through an image encoder so that we can extract the features. The encoders can be of different types, whether it's a ResNet 152 or ResNext, or maybe a faster RCNN, which will give us the bounding boxes for different objects in the image. Then for the text, we can have different type of text encoders. Similarly, the encoders may be like BERT, Roberta models, or even GloVe, fast text, and XLMR models. And similarly, for if there are other modalities like say OCR or any other modalities, we can have a modality encoder for each of these. So once we have the encoder outputs, we do a fusion. So the fusions can be of different types, whether it's an early fusion or late fusion. So we can use different type of fusion encoders for this case, whether it can be a transformers or like different type of late fusion models, or even we can do like attention fusion or different other types. So the output of the fusion is fed into a head. So the head can be either a classification head or a pre-training head, depending upon the task, or maybe also some other type of heads, like for image captioning, you will need to have like a generative head. So let's see some task-specific example. So for visual question answering, this is an example input. You have an image and accompanied by a question. So we feed this image and question into the model, and the model outputs some features. And then on top of those features, we have a classification head, which will classify the question and like classify into the answer space. So for specifically for this question, which lane is closed, it answers as left. So let's now dive into our tutorial. So I'll start from the modeling part. So where we'll build a model for the OK-VQA task. So so here the task Okay, so let's get started with the tutorial. So here we'll build a model for the OK-VQA task. The task requires a model to take multiple input modalities. So as we have seen in the dataset, it takes a text question as well as the images. So MMF has built-in support for building these type of multimodal, building models for these type of multimodal tasks, and offers a tons of features to easily build this type of models. So in this specific case, use case, we'll build a transformer-based model for the OK-VQA task. So first, we need to build the different type of encoders and also a multimodal embedding class, which can like take these encoder outputs and build a joint embedding for our different modalities. So for the multimodal, so for the modality encoders, we have the text modality as well as the image modality. So for the text modality, our dataset processors already can pre-process the text and output the tokens using a different type of text encoders, whether it's a BERT based or maybe it's a GLOVE based. So we can specify these different text encoders in our configuration system, which we'll do it later, and I'll explain it later again. So for the image part, we'll define a new image encoder class, which takes in a multimodal encoder based class, which is actually available already provided by MMF. And it builds the encoder, image encoder, based on the parameters we specify in our configs. So the configuration parameters can specify what type of image encoder we want. Like maybe it's a ResNet 50 or a ResNet 152, and maybe other type of parameters like how many features we want as output, or like the type of pooling and all those. So once we have defined the image encoder, let's next move to the MMF transformer embeddings. So this is the embeddings class that we are defining, which will take in the output of these different encoders, and then they will create some embeddings, which will be later concatenated into a joint embedding for both the different modalities. So the encoding, so the embedding class takes the two modalities, image and text, and each will have 3 different type of tokens. So these tokens are the input ID tokens. So these are the either the text tokens that are generated by the text encoder, or the image features, which are generated by our which will be generated by our image encoder. Next is the position ID tokens. So these are the positions of the text tokens, or like the image features. So if we have a text sentence, so each of the word in the sentence will be will have a position, like say from beginning it will be like 1, 2, 3, and so on. And the last type of tokens is the segment ID tokens. So the segment ID tokens specify what type of modality it is. So for text, it will say it will have a segment ID as say 0, and for image, it will have a segment ID as 1. So that just we can differentiate between the modalities. Next, let's move on to the implementation of the MMF transformer embeddings class. So in the initialization method, we actually initialize the weights of the text embeddings from the base transformer models embeddings. So this is done just so that we don't have to like retrain the embeddings again, and we can use the already trained transformer embeddings. So we are using these transformer embeddings, word embeddings, as well as the position embeddings. And then we initialize like layer norms and dropouts. Similarly, for the image embeddings, we define a new sequential which takes like 2 layers. One is a linear layer and then a layer norm. And we also have the image position embeddings, and also followed by image layer norm and dropout. For the token type embeddings, or by token type actually we mean the segment embeddings, we again use the based transformer models embeddings. So the forward pass of this, or the forward method of this embeddings class, it basically takes in the input IDs, the position IDs and segment IDs for both these modalities. So these all the input parameters are defined as a dictionary of string tensor. So the keys will be like which modality it is, which modality is specifying. So for text will be string will be text, and the corresponding tensor for the embedding, corresponding tensor for the input token. And similarly for position IDs and segment IDs. So we pass all these different inputs and IDs, or like input and tokens, through our different layers that we have specified here in the init method, and we get the embeddings. So let's first go to the text part. So the text embeddings will generate the word embeddings, the position embeddings, and the segment type embeddings, which we are saying here is text type embeddings. And then we'll do an addition and then pass them to the layer norm. And then again a dropout. So next we go to the how the image embeddings are generated. Similarly, we'll pass them we'll generate first the image input embeddings, and then we'll also have image position embeddings, and then last we'll have the image token type embeddings. And once we have all of these, what in the end what we'll do is we will concatenate the embeddings for both the text and the image, so that we have a joint embedding. And this will be passed later on, passed to our transformer model. So let's now move on to the transformer based multimodal model, which we'll be implementing. So MMF actually comes out of the box with the required boilerplate structure to build these type of models. So MMF has a base transformer class, which comes with some very basic building blocks to easily like import transformer models from 𝗰𝗵𝗹𝗵𝗁 transformers library. And we can modify them according to our use case and build them for like some multimodal tasks. So extending this base class is very easy, and we'll just need to implement the methods which are specific to our model, and we can just override them and like customize them according to our need. So these basic building blocks for these type of models are, we need like a transformer base. Second, we need encoders. Third, we need the embeddings. And fourth, we need the different type of heads, whether it's a classification or a pre-training head, or maybe it might be some other generative heads as well. And last, we can also specify some losses that we want to apply to the outputs. So let's take an example for like our use case. So here, what we want to do is we want to build a transformer. Let's say we want the base to be a BERT base model. So the base transformer class actually comes with the build transformer method, which if you just specify the name of the model in your config, such as like here, transformer base as a BERT base uncased, and it will automatically load the model from 𝗰𝗵𝗹𝗵𝗁 transformers library along with the pre-trained weights. So we don't need to like change anything there. Just specify the name of the model and it will be automatically loaded. And then we define like how the forward pass can be implemented using this base transformer class. We'll go into more detail about each of this step, but here is a model flow that we can see. First, we'll pre-process the sample, then we'll generate the embeddings, then we'll generate some attention masks, pass them everything into the base transformer models encoder. And the output of the encoder is passed to the heads, like whether it's a classification or pre-training. And then we'll finally post-process the output as required. And the forward pass actually outputs a dict string tensor. The string will be maybe scores, and then the tensor will be the output scores for the classification problem. So let's dive into the model now. So most of the code is already like well commented. So you can also like read through it and understand what each particular section is doing. So let's focus on the important ones. So the build encoder method here. So here we are building the image encoder and initializing it with the image encoder class that we had built earlier in the previous section. Similarly, build embeddings. We are using the MMF transformer embeddings that we have built earlier. And next is the build the heads. So here for this task, it's a classification type of problem. So we have an image and a question, and we want to do a classification over the answer space. So we'll build a classifier here. So classifier is an sequential which takes a bird pooler. So we are using a bird pooler, which is a pooling layer, which is used by bird, and then a bird model. And so since our transformer base is a bird model, we'll use the same. And then we have a dropout and then a bird prediction at transform. So it's basically a linear layer followed by an activation and then a layer norm. So activation can be 𝗀𝘆𝑆, 𝗀, or like 10H. So, and then lastly, we'll have a linear layer, which will just project the hidden output into the number of classification labels that we need or there are there in the answer space. So the next important method is the pre-process the sample. So here we are trying to standardize the inputs to the inputs to our transformer base model. So the way we are trying to do it is we define this base transformer input type object. So which takes in like input IDs and which takes in position IDs, which takes in segment IDs and masks for all the different types of modalities. So just in case you want to define a new model which has more than say 2 modalities of text and image, you can still use these base transformer input type object and pass on your modalities into these different IDs, and by just adding them to their dictionaries. So we build the different type of IDs here in this method, and in the end we'll just create a base transformer input type object and return it from here. And let's next go to the forward pass. So first we'll pre-process the sample and we'll pass this output to our embeddings layer. And then we get the embedding outputs. And then we also generate the attention mask. So attention mask in this case will be same because we are not actually masking anything. And since it's a classification task and we are not doing any masked modeling for pre-training or anything. And then we'll pass these embedding outputs as well as the attention mask to our transformers encoder. So the encoder will return us like the different outputs or like what we call is the encoder layers. So, and then we actually use, so in the BERT models, we actually use the output of the CLS token and encoder layer, and which is actually the first one. So we'll pass that to our classification layer. So the classification layer will give us some output, which will be actually the scores for like the different labels we have in our answer space. And then we'll post-process that output using the post-process output method. So here we are just like reshaping our output, but we can also, if you want to also apply some type of new losses or anything, you can do it here. And the output of this forward pass is a dig string tensor. So, and in this case, it's string is scores and the tensor is like the output scores. So here we have finished like defining our class. Sorry. Next, let's move on to the important thing of how we can specify the configurations for this model. So MMF transformer, so what we'll do here is we are actually building a dictionary and then we're saving it as a YAML file. So MMF takes in, we can use YAML files when we run the experiments or like inference, and then the different CLI commands can take these files as input. So we are specifying this dictionary where we are specifying different type of parameters for the model. So as we discussed earlier, the transformer base will be a bird base and case type, which is basically a bird base model. And our model will automatically load that model from Hugging Face library and along with the pre-trained weights. Then there are some other important parameters like say the image encoder, where we specify what type of encoder we need and also different type of parameters for that, like how many output features or what is the pooling type we require for that. Then we have the experiment configuration, or also user configuration, as Aman already mentioned in his configuration slides. So here we, basically it's the configuration for your experiment, or like the particular task you are currently doing. So we specify different types of configurations, say for schedulers, or also like optimizers, or like different type of training parameters. So one thing important to note here is that, as we mentioned earlier, that we'll be using a BERT-based encoder for the text part. So here, since OK-VQA dataset by default has a text processor which takes a GloVe text processor, so we need to override it with a BERT tokenizer, or a BERT-based encoder. So we do this in order to, so since our model is using a BERT model, so we use the same tokenizer for it because it will have the same vocabulary. So we can override that here in our user or experiment config. We also specify some specific configurations for our model, which is like the number of labels in our answer space, and also like type of loss we want to apply, which is a 𝗫𝗁𝗃𝗃 loss. And similarly, we'll save this as a YAML file so that we can run our experiments. So next section is running the experiment. So I won't run the experiment since it will take like a lot of time to finish it. So, but you can run it and see how the model trains. And next is like the inference on the validation set. So we have already provided a pre-trained model, so which we have trained with exactly the same configuration that's available, that is given here. So if you train a model, you should get the same model. So we are providing it here, and it's already downloaded in my runtime. And we can run the inference on the validation set. So I will also leave it to you to run it because it takes a little bit of time. So next what we'll see is how we can do some evaluation on some test samples from the OK-VQA dataset. So first we'll just build some necessary configuration processors and load the state dict to the model. And then we'll, once since it's running, so then what we'll do is we'll pass in a image URL and also the accompanying text, and we'll see what the model answers. So here is the image. So it's a horse, and the question was, which sport requires riding on the animal depicted? And the model answers race. So I think it's pretty reasonable answer. So we come to the end of the tutorial here. I'll move back to the slides. So as we see, we can build the different data sets and models with MMF pretty easily, because MMF provides all the building blocks that are required to build these models. So MMF comes with like endless possibilities, and we already have like a lot of research being built on top of MMF. So some of the examples are 𝗵𝗿𝗃𝗃𝗃, TeXt-VQA, LoRa, BUTD, and PyTorch models. Also, the Hateful Memes challenge is now hosted on MMF. And there are some other papers like Are We Training It Right, then text caps. And also we have some latest state-of-the-art models, multimodal transformer-based models like 𝗰𝗵𝗹𝗶𝗁𝗃 and 𝗰𝗵𝗹𝗶𝗁𝗃 implemented in MMF. So thank you so much. If you have stuck with us till the end of the tutorial, thank you a lot. And so we welcome everyone to contribute to MMF and add your models, your new models and new data sets to MMF and help the community grow. So MMF has been possible due to a collaboration between a lot of teams and folks, both at Facebook as well as external. And we thank everyone. And here are some resources. Please visit the links, and also you can like run the tutorial again using the Colab notebook that we have shared. Thank you.